All right. Well, I want to welcome everybody. My name's Ethan Brisby. I am the founder of Shift Enterprise Academy. We are a US based ed tech company with an expanding footprint in East Africa. And so what we're doing this month for February is we're celebrating Black History Month. It dawned on me since I've been in East Africa that you know what? Black history is actually also African history. And so today with us, we have Mr. Primus Eugene Jackson. He spent quite a few decades working so that mankind could go and experience life in space. And so I'm not going to give you a long, extended introduction about him because he's going to tell you a bit about the work that he's done. But what we will get the chance to do is go one on one and sort of interview him after he gives us this brief presentation. So, without further ado, I want to pass it over to you, Mr. Jackson. If you would go ahead and kind of let us know what you've prepared for us, and I look forward to chatting with you a little bit more after you do your presentation.
All right, thank you. Thank you for the opportunity to speak to Africa. It's quite an honor. I look at the map here on the right and I think, wow, I'm possibly talking to people all over Africa. Will eventually see this presentation. I love to travel. I haven't done a lot of traveling in the middle of Africa, but I plan to get around to it, and I'm kind of honored. I enjoy doing this. I think it kind of makes me a better person in the long run. So hopefully all this makes sense. So what I thought I'd do is tell you a little bit about me, and then I'll take three programs that I worked on while I was at Honeywell, and then I'll share some of my wisdom that I've picked up over the years, and then we'll close it out with some questions. If you have any questions, hold them till the end, and I'll come back and I'll answer them. So I used to live in a place called St. Petersburg, Florida, which is right here. I was born and raised here. And one of the things I always wanted to do was live in Galveston. Because when I was a little kid, it was like Galveston, Texas, an island. And a hurricane would come in the Gulf, and I'd say, wow, I want to go Galveston. So actually, I ended up living in Galveston while I was working at Kennedy Space Center. So it wasn't like Gilligan's Island. I was disappointed in that sense, but Galveston is a pretty neat place. That's where they had the original Juneteenth reading of the Declaration. Every year they do reenact that. So when I was a little boy, one of the things I really enjoyed doing, looking up at the sky and looking up at the stars. And we would take a trip up north to a place called Quincy, Florida, every year. And Mom say I would fall asleep on the car looking up at the sky. And I didn't know what I was looking at because I was just a little kid. And I see these comets, they were comets and asteroids. And it was out in the country, so you could see real clear. And it was like, as I got older, I started reading encyclopedias my dad had bought, starting from A all the way through. And I found comets and asteroids and Earth and all the planets. And I memorized the distance between all the planets. It was 33, 67, 93, just a million miles between the first four planets all the way out to Pluto. When I was in elementary school, I came up with this little science project, and I won first prize. It didn't look like this. This is a picture I found it, but it was similar. And it was all the planets, and I used a motor from a phonograph to make them move and rotate. And I won, I think it was first prize that fifth, sixth grade. And that's me as a little boy. I was kind of cute then, I guess you'd say. But when I would drive back from Quincy back to our hometown in South in St. Petersburg, I would always see this sign that said, "Come join Honeywell space program." And my older brother would always say, "They're not going to let any color people work there." Every year from probably 10 to 12, 13, I would hear him say that. And I would cry because I thought, I want to work in Honeywell. I want to work on the space program. But that was kind of disappointing. As I was growing up, I would always ask my mom, I needed a meter because I was studying electronics. I need a calculator, and I want to go see this Apollo launch. And I would beg my mom and Dad, let me have these toys. I need him to learn. And my dad would say, let the boy have it. That's for his education. Take it out of grocery money. And my mom never worked out of the house, so we didn't have much money, but we'd find money for me to go. And I went on a field trip over to Kennedy Space Center when I was a teenager, and I saw this Apollo launch. And when I saw that, I knew what I wanted to do. I really loved space work, and I kept studying and studying and studying until I eventually, in 1968, made it to Honeywell. 1968 was a really transition year. A lot of things went on in 1968 in the United States. Martin Luther King was assassinated, R.F. Kennedy, and had more Apollo launches. But the interesting thing about my career was I started working at Honeywell before man officially landed on the moon. And I got to go and see some of the hardware that ended up on Apollo as I was working at Honeywell. I said, wow, this is going into space. Well, that was kind of a transition year. But one of the saddest things that happened was I lost my mom in 1968. I think it was October 1968. And I was barely 19 years old. And my teachers, I went back to talk to my teacher, say, look, I want to go back to college, but Honeywell was want to let me stay there. So in 1968, I had to make a decision. My dad was kind of disappointing in sending boys to college. My two sisters went on, but my older brother, he didn't do too well. He just spent money. So he said, I'm not sending any more boys to college. So I had to figure out how to do it on my own. So Honeywell said, you can stay here and we're going to pay for your college education. So I stayed at Honeywell and worked full time, and went to school part time, and eventually finished. And then I went to work at Honeywell in May '68, and I lost my mom a few months later. As a result of losing my mom, they had sympathy for us, so I stayed there and worked. And I finished college, and through the years, I've had many assignments. After finishing, I got a degree in computers and computer systems, electronics, and stuff. So I was assistant engineer. These some old business cards I dug up. At Houston, I was assistant engineering manager. I had people working on space station, integrating Honeywell hardware in the space station and test equipment. I was a staff engineer, and lastly, I was a principal systems engineer. So I thought what I would do is share with you some of the programs and a little detail about some of the programs, not a lot of technical stuff, but just enough to inspire you and make you curious. All right, so here are some of the major programs that I worked on during my career. On the left, Space Shuttle. That was the main engine program. I'll get into that. Between Space Station and Space Shuttle, the space program kind of slowed down. So I had to find something to do. So I transitioned to the military side of things, and I worked on F-15 electronic countermeasure systems in Saudi Arabia. I don't mention that much, but I'll tell you what that's about. And then when I came back, so this was Space Shuttle was probably 7 years. This was 3 years. Space Station was 17 years. And I was working on Orion for a long time, which was a replacement for the Space Shuttle. The last program I worked on was a space suit program. And what that was about is trying to make a very high-tech spacesuit with a lot of electronics in it. A heads-up display and this little pad on an arm so the astronaut could have all this information theoretically as he was walking on the moon or Mars or spacewalk. They wanted the astronaut to have all that information on him. So it was a challenge. And that program kind of got canceled as the budgets got cut. I'm not sure what's going on with it now. They probably built a lesser version of it, but that was not so sophisticated. So here are 3 programs that I was going to talk about. As a system engineer, these are the kind of things you do. The first thing you do is initial requirements. And what that means is you gather all the stakeholders and you say, okay, what do you want this system to do? And how do you want it to operate? And what it should look like? How much should it weigh? What's the software? What's the throughput? And then you build a prototype, and then the customer evaluates that, and you go back to design and change it. And eventually you get satisfaction from the customer that okay, we got it nailed down, we're ready, we're prototype, we're ready to deploy it to the field and test it and maintain it. So the initial task is to gather all these documents and all this information to go build something. Well, here's an example of system requirements. Now, this is going to be kind of high level, what I'll explain to you in a minute. It's not all that technical. I mean, it's very technical, but I'll hopefully explain it very well. This is the space shuttle main engine. And over here, right there, is the main engine controller. And what it does is monitor the temperatures, the pressures, the speed, pump speeds, the main chamber pressure, all those things. So the engine was built by a company called Rocketdyne, and Honeywell built this box controller. And so here are the requirements on the left here, basically high level requirements. And it talks about how main fuel valve opening, the main oxygen valve opening, oxygen pre-burn oxygen valve, all these valves, all this is requirements as to what this controller and software has to do on that engine. So the documents go between Honeywell and Rocketdyne, Rocketdyne and Honeywell, and NASA's in the loop as you develop this product. And here's the valve position that we're being explained as requirement. The main fuel valve, I'll explain in a minute what I'm talking about here. The main fuel valve, the coolant control valve, fuel pre-burn oxygen valve, oxygen pre-burn valve, and there's main oxygen valve. So it's 5 valves that have to be controlled 0 to 100%, along with a bunch of temperatures, a whole lot of pressures, a lot of things. So this Friday, I'm going to explain it. It's the main engine flow, propellant flow. What happens is you have, this is on the left is the hydrogen pump, on the right is the oxygen pump. So what happens is, in the middle, all these hydrogen and oxygen come together, and there's an igniter that sparks the whole process, and the engine runs. And as it runs, what happens is the pre-valve, here's the propellant. As this hot gases flow across these turbines, it pumps from the main external tank above down this side into the high pressure pump, and that pumps it into the main chamber and the coolant valve. I'll show you in a minute. You'll see these valves in this on this engine. There are lines that hydrogen flows through to keep it cool. Same thing on the other side. Low pressure pump, hot gases flow across the turbines, and the pump turns, which pumps the oxygen into the oxygen pre-burn, the high pressure oxygen pump, which pumps the gas into the main chamber. So all this happens and is all monitored by the main engine controller. Here's a valve. That would be a coolant control valve that controls the coolant going in and out of these veins. Here's a valve that would be a main oxygen valve. This is the valve, main fuel valve, main oxygen valve, and it's keep trying to maintain a ratio of 6 to 1, 6 based on the density. 6 parts of hydrogen, 1 part of oxygen. So that's basically the flow of the propellants in the engine. All it is gases flowing across turbines, and the turbines turn, creating the pump action to go move the fluid further along. We can talk about that later, with questions. Here's the actual main engine controller. It weighed about 200 pounds, and it's basically what we call a dual redundant system. At that time, it was probably built in 78, 79. Believe it or not, it was on a 16K of memory in both channels, A and B. Nowadays, remember, you can get megs in a jump drive. So it was built on a processor, and the processor was like 2 or 3 boards and then 5 or 6 boards. So now that main engine controller, it probably would need to be the same weight because it got to ride on the engine, but internally you can put more electronics in it now. I haven't kept up with the program because I've been retired and not working on that program. Now here's the block diagram of that engine controller. Within this bottom chart here is the electronics. Notice it's redundant. Input electronics, there's 2 of them. Computer interface, digital, power supply, all is redundant. Everything's redundant. in the space program, there's always a backup, sometimes triple redundancy. And all this up here is the general computer in the orbiter, engine interface, all this is other electronics, your igniters, things like that. Igniters is what sparks the combustion in the main engine. You'll see that in a few slides. Hopefully that plays well. Here is what the key to the whole thing is: the A and B channels. A channel is running in control, and then what it has to do is reset a counter, and we call that a watchdog timer. And what happens is it's set to 1,000 and it starts counting down. And hopefully, if the controller is still in control, it hadn't got caught up in a loop, it'll reset that counter. As you see here, if you can see my pointer, in the second column, it goes all the way. But here on the last column on the right, you notice it hits 0. When it hits 0, that means it's out of control. It's not able to reset that counter back to 1,000 every time. It's running at 1,000 times a second, 1 millisecond clocks. So every time it counts down, it gets maybe 80, it resets it, 75 resets it. But if it doesn't get around to executing the code to reset it, it'll hit 0, and then you notice B takes over. So this electronics that I was showing you here, is an A side and a B side. B side takes over. So basically, when we got an engine and mounted a controller, here's the test that we'd have to run. The first test is a 1.5 second test, which is just spark it and make sure the pumps torque and move. And then there's a 10-second test. The flight profile is the 8-minute test. The engine, if you ever notice a shuttle launch, it have to run for 8 minutes to get to orbit. 2 minutes, the SRBs separate, if you ever want to separate, and the engines, 3 engines have to continue to run. So, and here's what a test stand looks like. We had 2 test stands, an A test stand and a B test stand. On the right, that was simulating running the engine into a vacuum chamber. When you get up in space, there's less density, more of a vacuum. So you're firing the engine into a what they call a flame bucket. And you can very well, you can see the main engine controller mounted there very clearly. Hopefully this works. This is a test. So you're standing back, there's a control center, and the engine's commanded to run, and it runs for, in this case, I think 8 minutes. And I'll stop it here. This is the same thing. This is the other one, the A2 test, firing into a flame bucket. What went wrong? Now here's an example of requirements that didn't get properly communicated. Remember, everything starts with requirements. During a test, we had several engine explosions because of testing, but someone had to be outside with a camera and they caught this explosion. And what happened was, remember, there's 5 valves that have to be controlled. On the left here is a successful test. On the right is a not so engine explosion. And you notice what happened in this case, next slide, is the main chamber pressure. So the goal is to get the main chamber pressure up to look like 28,000 PSI. In this case, it didn't quite make it. So what happened was the main chamber pressure accumulated some ice in the cavity where the pressure transducer was. And because of that, the engine tried to throttle up. It said, okay, we're supposed to be at 28,000 RPMs and we're not there yet. So let's just throttle up until we get there. Well, in the process of throttling up, it shook the engine, the pump shook apart. You know, like tires on your car, they're calibrated to not vibrate a certain revolution per second. The same thing with these huge pumps. They pumps probably weigh 200 pounds. They're not designed to run above a certain RPM. They're designed to operate smoothly at a certain level. So when the main chamber pressure was misread, it throttled the engine up so high that it shook itself apart. So on the left is the main engine controller, and right under my arms, you see the high pressure fuel pump. On the right, after the explosion, you don't see the high pressure fuel pump. It would be right here if it was here. And this is the oxygen side. We know that because on the oxygen side, they have this spear called a whole go accumulator. And that's half gas and half liquid oxygen. They make it a more smooth ride. So after all that, we had to go back and redo the requirement and say, well, what went wrong? Well, what went wrong was nobody ever thought to put an upper limit on the valve positions. And it just tried to throttle itself up to get to that pressure, and therefore it shook itself apart. And so I moved 3 years later after all the testing. I finally made it to my dream location, Kennedy Space Center. I always wanted to work at Kennedy Space Center all my life. I dreamed of it. And when I got there, it was like, it was the most beautiful thing, you know. Well, so during that first launch, it was in not the launch control center, but the backup engineering room, and had on the headset. And we had a failure of a temperature sensor, but it was not one that was in the control loop. So I said, that's not engine failure, that's just a transducer failure. So when the orbiter came back, the NASA guy put this together and gave me the transducer that failed, which I thought was pretty cool from the first launch. And that was in April of 1981. So the next program was electronic countermeasure programs in Saudi Arabia. I stayed there 3 years, and the basic task was to train the Saudis on the ECM system, and that involved test equipment and several boxes on the several boxes on the airplane. One called a radar, one was a jammer. So what happens in that system is the radar warning receiver scans the air, and it sees the frequency that looks like what has been programmed to be a missile, and it tunes the next box to that frequency, thereby jamming the signal. That would be like your favorite radio station, and then someone tries to tune to the same radio station. Neither one of you could probably operate properly because the frequency is being jammed. So it was the top round circuit unjammed. It said, okay, we got an air-to-air threat, and we got a surface-to-air threat. Missiles aimed at us. So the threat box jams those signals. So the pilot says, okay, I'm jammed, and he can't hit me, he can't shoot me because the signal is jammed. So I don't want to spend a lot of time on this, but basically, the radio frequencies is what we're talking about. And in the gigahertz range, we have what do you call it? The electronic countermeasure systems. And if you ever done any thinking about it, here's amplitude modulation, frequency modulation. And when you get into gigahertz, you can have all of those modulations. Modulation simply means you're going to inject your intelligence on a carrier frequency. And amplitude modulation is basically what you see on the right top there. That's the amplitude changing, but the frequency stays the same over here. The frequency stays the same. So that's what's called amplitude modulation. In other words, when you speak, the signal is changing the amplitude, and then the other end, it demodulates it, it takes out the frequency, and you get your voice. FM is the same thing, except the frequency is modulated. On the bottom, you see the frequency changes as you speak. The red wave there imposes with this frequency, and you get a frequency modulation. So modulation is just means changing, it means combining a carrier frequency with some intelligence. And that is the same thing that happens with electronic countermeasure systems. someone has decided to use a certain frequency. So what we have to do is go out and research the skies and find out what frequencies they're using, and we put that into the systems and jam them. There are other types of modulations. There's digital modulations. You can notice here the shifting in the amplitude here. There's frequency shift modulation. So modulations is the key to all communications. It's just different kinds of modulation. And they have digital modulations and amplitude modulation. They call them analog modulation. What I showed you previously, analog, and this is digital. And here's just another display of the scanner scanning the skies. It sees these threats and sends a signal to the jammer, and it jams those frequencies. Pretty basic, but it gets complicated when you get into how the boxes work. But basically, that's how it works. That was when I really discovered I enjoyed traveling. Every 4 months, you get a vacation, and it was pretty cool. I got to travel the world. The last project is the space station that I'm going to explain a little bit about it. I worked on that for 17 years because it changed names and evolved over the years. These are computers. Notice there's a shadow behind it. This is called a distributed operating system. A distributed computer system. And there's backups and there's redundancies. There's 54 of these boxes that are networked together to talk to each other. On the right here, GNC, Guidance, Navigation, and Control. RS, Russian spaceship. These are, we talked to, all these boxes have been in Russian FGB, which stands for Functional Cargo Block. And you have, what do you call it, Japanese experimental module. Environmental control, where is that? So all these boxes can network together to operate on the space station. Hopefully this is not too confusing, but hopefully you get a chance to ask questions and I can explain further if we need to. So these are just pictures. I love space station. I was walking through the airport in Hobby and I just couldn't help but hug the space station. People probably thought I was going crazy, but I enjoyed that program a lot. Now, here's some wisdom. And I think I'm qualified to give you a little wisdom because I've been there 40 years, actually 42 years. This is just my opinion. And I say, don't allow someone else to define you, define yourself. Here in the United States, I'm not sure how everything works in your countries, but I always say, if it bleeds, it leads in the news. And people get an impression of African Americans sometimes strictly from what they see on the news. So I always say, when you interact with people, open up, talk to them, let them know that you have common sense, you're intelligent, you're not what they saw on the news, crime or whatever, drugs or whatever. Speak for yourself. Next one, race is not as big a problem as it used to be because a lot of people are expiring and the younger generations coming through. And I don't see a lot. It's not racist. It's not as bad as when I started in 1968. Nowadays, if you have this knowledge skill, you can probably make it. If you're working in an office, if you're working in an office, don't get involved with the politics and the name calling and try to operate above board. Stay out of the fray, so to speak. Be your own self, and don't let your environment make you do something that you regret or say something you regret. Always reach out and help others. To me, I'm like I said, I couldn't help but do this, and I'll do more based on what Ethan and Hannah wants me to do, because I do like to travel. I'll show that on another slide. And to me, we all have to help. All of us in the diaspora have to help each other. Otherwise, if we don't do it, no one else is going to do it. Don't be afraid to venture outside your comfort zone. Now, this is to say, if you got a degree in computer science, you need to know everything you need, all the applications that are in your office. I used to work with a guy who said, I don't know Excel, I don't know Word, I don't want to know them. You can't do that. When they hire you, you got to know every tool that's in that office. Otherwise, they can't afford to hire somebody for each tool. There's a lot of applications out there now, particularly in the software development world and the requirements development world. There's a system that contain all the requirements. You got to learn that system. Always and never stop learning. The next one, always find ways to educate yourself. Nowadays, you can Google anything. You got Wikipedia, you got YouTube. There's knowledge out there. I'm not. I'm trying to get up to speed on AI, artificial intelligence, and quantum computers because I just want to keep up. I think it's nice to know, even though I don't think I'll be going back to work in those fields. It's just nice to know. Find some way to mentor people. Always try to find a way to help somebody else. It's like repeating myself, but hands-on, sit down. Like I did work with kids with robotics. After work, I would go work at high schools. I would go work with junior high school and these best and first robotics program. Right now, you get a lot of education through those programs because most of your major organizations, major robot, they're like corporations. You get in there, you do the robots, you do the software, you do the PowerPoint, you do design. So you come out of those programs with a lot of knowledge. I mean, you get more knowledge out of that, more useful knowledge out of that than you would in your classroom, really, because it's hands-on. Be mindful of your education, of your attitude. As they say, your attitude can influence your altitude. So don't get caught up and angry. I mean, if you get angry outside of work because in the United States and probably in all parts, you can get labeled and it's hard to erase that label. So finally, I'm going to say, this is my little formula: passion and goals. Set your goals, and do something that you really enjoy doing, you really want to do. Get rid of the attitude and learn from your failures, and you will be successful, in my opinion. Lastly, as I said, I love to travel. All the red dots are places I've been, and the yellow ones are places I'm going to go. Like March, the yellow ones, I go up the west coast of Africa and end up in Spain. So that's all I have to say. If you have any questions, we can entertain those questions at your leisure, whenever Ethan wants us to.
Wow. Wow. I was sitting here listening to your presentation and it's just so mind blowing. Thank you so much for sharing that knowledge. We're going to hit pause right here and then we're going to come back around and I'll lead with some questions. And then, of course, we'll give folks the chance to jump in there as well. But thank you so much. That's Mr. Primus Eugene Jackson, over 42 years doing some of the most extraordinary work that modern mankind has ever known. So I know some of that you probably like, hey, I would love to know more, whether it be systems engineering or just even just some personal questions or that incredible world map he just showed you. So we'll come back and give you the chance to speak with Mr. Jackson.
So I'll stop sharing this.
Yeah, that'll be good. I'm gonna find my button here to hit stop recording. Where is it at? There it is.